All right, so we're going to talk about chapter 6 now, which is where we start to talk about ionic and molecular compounds. We want to be able to differentiate between the two types of compounds. And then we'll talk about some of their properties and how we name them and things like that. To start, we have to know what an ion is before we can talk about an ionic compound. So we've talked about atoms before, and we've kind of mentioned the fact that ions can exist, but we haven't really defined them before. Atoms are going to generally try to lose, gain, or share electrons in an attempt to gain what's called an octet of electrons. That means that they want 8 electrons in their valence shell or in their outer shell. Okay. How they get those 8 electrons depends on whether they're going to form an ionic bond or a covalent bond. Or if it's a noble gas, they don't need to form a bond at all because they already have their 8 valence electrons. But some of the different properties of our elements determine whether they're more likely to form an ionic bond versus a covalent bond. So when we say the term ionic bond, we're talking about the type of bond that happens when your valence electrons of one of our metals are transferred to a nonmetal. Okay. So you have a full transfer of electrons that happens when ionic bonds form. With covalent bonds, this is going to happen when you have nonmetals that are forming a compound together. Nonmetals do not want to give away their electrons. And so when they come together to form compounds, instead they're going to share electrons in order to get that octet that they're looking for, which we can also refer to as a noble gas arrangement, meaning that they'll have the same valence number of electrons as a noble gas would. This is kind of the difference between what you would see in ionic bonding versus covalent bonding. When you have ionic bonding, you'll have a metal that has an electron it wants to get rid of, and it's going to donate that electron to the nonmetal. And this is the compound that would form. You'd have an ionic bond, which would essentially be the electrostatic attraction between the positively charged metal and the negatively charged nonmetal. And that's what's going to hold them together. When you have two nonmetals that want to form a bond, neither of them wants to get rid of their electron. So they're just going to get close enough to each other where they can both share the electron of the other one. And in that way, they're completing their own octet. So now each one has 8 electrons around it. And this is where that bond will happen, the covalent bond. So ions are going to form. Ions are what we are going to call the charged atoms. When an atom is not neutral, it's going to be considered an ion. And our ions can be either positive or negative. Our ions are going to be positive whenever they lose electrons. Okay, so if we have an atom that loses its electrons, then it's going to end up with a positive charge. This will be a positive ion. Our metals are going to be the elements that form positive ions, okay? We've talked about that a little bit in the last chapter when we looked at the trends on the periodic table, or not the last chapter, the chapter right before that. When we were looking at ionization energy and metallic character. Metals have very low ionization energies. Things with low ionization energies have an easier time losing their electrons. Okay. So they're going to readily lose their valence electrons to form positively charged ions. And the amount of electrons they're going to lose is going to be the same number of electrons, whatever number of electrons they need to lose to reach the same number of valence electrons as the nearest noble gas. Okay. If we look at our periodic table, we'll do like a little sketch here. It's not going to be perfect. And if you look at your actual periodic table, while I'm drawing this out, it'll make a little bit more sense. Let's say that we have sodium and we have magnesium over here. This is our third row of our periodic table. In our second row of our periodic table, we're going to have lithium and beryllium. And then over here, all the way on the other side, we're going to have neon. Okay. Neon has its atomic number 10, right? So it's going to have 10 protons and 10 electrons. And if we look at its number of valence electrons, it's going to have 8 valence electrons. Sodium is atomic number 11. Magnesium is atomic number 12. Sodium wants the same number of electrons as neon. So how many electrons does sodium have to lose to end up with neon's number of electrons? It has to lose 1 electron. So if sodium loses 1 electron, that means that sodium is going to have, it's still going to have 11 protons because the number of protons can't change, but it's only going to have 10 electrons. And so that means that sodium is going to have a +1 charge. Magnesium is also a metal, and it's also going to be trying to get the same number of electrons as the nearest noble gas, which is always the noble gas that comes right before it on the periodic table. So magnesium starts out with 12 protons, and it wants to end up with 10 protons, or with 10 electrons, sorry. So if it has 12 protons and it only has 10 electrons, well, now it's going to end up with a +2 charge. Okay. That's how we're going to be able to figure out how many charges or what the overall charge of our different metals is going to end up at. We're going to look at how many protons they have, and we're going to look at how many electrons they'll end up with once they're done losing their electrons. And then we'll be able to determine the charge from that. Another name for a positively charged ion that you want to be familiar with is the term cation. Right down here. A positively charged ion called a cation is named by its element name. So cation is the overall name that we give to anything that is positively charged. Okay, so the sodium ion and the magnesium ion from our example, both of those are cations. And this is again showing what happens during that process. So here we have sodium. Its valence electron is going to be the electron that's furthest away from the nucleus. And this is the electron it's going to lose in order to become an ion. When it loses that electron, its size is going to decrease significantly. And now it only has 11 protons and 10 electrons. And you see how it's structured here, 1s2, 2s2, 2p6. This is the same electron configuration that you would get for the element neon. They're showing the same thing for magnesium here. Magnesium has 2 valence electrons. So when it loses its electrons, again, it's going to shrink down, get smaller. And it's also going to end up with the same valence electron configuration as neon. Our negative ions, on the other hand, are going to result when we gain electrons. Okay. Again, we can never change the proton numbers, but we can change electron numbers. Our nonmetals are going to be the things that will gain electrons. Okay, so if it's a metal, it loses electrons. If it's a nonmetal, it gains electrons. Our nonmetals are going to have really high ionization energies. So it's going to take a lot of energy to try to remove an electron, which is why they don't lose them. Instead, they're going to gain electrons in order to form ions that have a negative charge. And they are also going to be looking to have the same number of electrons as the nearest noble gas. But when we're working with our nonmetals, we're going to be looking for the noble gas that comes directly after our nonmetal. Unlike our metals, when we looked for the noble gas that came right before it. Negatively charged ions are called anions. And unlike cations, where we don't change the name of the element when we're referring to the ion, for our negatively charged ions, we're going to keep the first syllable of the element name, but we're going to change the ending to IDE. Okay, so I'll show you when we're looking at some actual examples of this. Um, so they have a few examples of different ions that they're visualizing for you here. I want to sketch them out kind of how we did for the other ones though. So let's look at this. Again, you can use your periodic table to like supplement this so that you're not just looking at my ridiculous pictures here. What I'm specifically sketching out here is the end of row 3 on your periodic table. Okay, and this is going to be phosphorus, sulfur, chlorine, and argon. Okay, argon, atomic number 18, 17, 16, and 15. Remember that when you're looking at your periodic table, you can look at the group number to figure out how many valence electrons each thing has. Rewrote CO. 7A, 8A. What you can also look at is, all right, I've got phosphorus here. Phosphorus is in group 5A, so phosphorus has 5 valence electrons. Okay, and like we already said, everything wants 8 valence electrons. Everything's trying to be like a noble gas. So if phosphorus has 5 valence electrons, it needs to gain 3 valence electrons to get to 8 valence electrons. Okay. If it's adding 3 valence electrons to itself, that means that its charge is going to get more negative by 3. So instead of being neutral, it's going to have a charge of -3. For sulfur, sulfur has 6 valence electrons because it's in group 6A. So it needs to gain just 2 electrons to get to 8 valence overall. So sulfur is going to have an overall charge of -2. Okay. For chlorine, it's in group 7A, so it has 7 valence electrons. So chlorine only has to gain 1 more electron to get to 8. So chlorine is going to have a charge of -1 because it only needs 1 more electron. Every electron that you add is another negative charge that you add. Okay. But look at what that means in terms of determining your charge values for your nonmetals. Okay. And this is, again, this is for nonmetals because nonmetals are our negative ions. For our nonmetals, we can look at our group number. We can subtract 8, and that's going to give us the charge of our anion. So everything that's in group 5A, I'm going to subtract 8 from that. Everything that's in group 5A that's a nonmetal is going to have a -3 charge. Everything that's in group 6A, I'll subtract 8. Everything in group 6A that's a nonmetal is going to have a -2 charge. Everything that's in group 7A that's a nonmetal is going to have a -1 charge. Okay. What you're going to notice for your metals, which I didn't write out before, so I'm going to write it out now. we mentioned it, but I didn't sketch it out here the same way that I just did for the non-metals. For our metals, which are in group 1A and group 2A, and then we have aluminum also, this is gonna work for. But we're only gonna really pay attention for it for aluminum because the other metals can get a little bit strange sometimes. But remember that just like with our nonmetals, the number of our group tells us the number of valence electrons that our atom has. Okay. So everything that's in group 1A has one valence electron that it loses. And so if it loses one valence electron, then everything in group 1A is going to have a +1 charge because they're all going to lose one valence electron. Everything that's in group 2A has two valence electrons that they lose. So all of your metals that are in group 2A are going to have a +2 charge because they're going to lose two valence electrons. And then aluminum is in group 3A. It has three valence electrons that it's going to lose. I'm going to put aluminum here specifically. So aluminum is always going to have a +3 charge because it's always going to lose three valence electrons. So your metals always end up with positive charges, and their positive charges are the same number as their group number. With your nonmetals, they always have a negative charge. And to figure out their charges, you could take their group number and subtract 8 from it, and it will tell you what the charge is. Okay. It's important to know what the charges are, especially when we're making up our ionic compounds. We're going to look back at the slides so that you can see some of the common ions for the different atoms can form. But you'll see the correlation here for our metals. Everything that's in group 1A here all has a +1 charge. If there's no number after the plus sign, you can assume that it means 1. The same thing for the minus signs. If there's no number, you can assume that it's a number 1. Everything that's in group 2A, they all have +2 charges. Everything that's in aluminum in group 3A has a +3 charge. And on our non-metal sides, you'll notice that the stuff that's in group 5A, they have -3 because 5 minus 8 is -3. In group 6A, -2. And then in group 7A, all of these are -1. And you'll see that the names of the anions are negatively charged ions. Remember, they keep the first syllable of your element, and then the IDE ending is going to be put on there instead of the regular ending. So instead of nitrogen, this is going to be called the nitride ion. Instead of oxygen, this is called the oxide ion. Okay? That's only true for the anions. For your cations that are positively charged, the names stay exactly the same. This is just another summary of what we just saw there. Our metals are going to be losing electrons. That's why they're positive. Our nonmetals are gaining electrons. That's why they're negative. And we can also see how ions are important to our body function. Sodium and potassium in particular, they deal with a lot of regulation inside of the body. You have those ion transport channels that are going to be regulated by sodium and potassium ions. There's also other ions that are present in things like your bones, your muscles, nerve control, things that are part of, again, how your body is going to function. Let's take a look at some examples though. Our first example, we're going to write the formula and the symbol for an ion with 16 protons and 18 electrons. Writing a symbol for an ion is similar to what we've done previously, but we don't have to include the mass number that we've included previously in our symbols, because remember that mass numbers are specific to certain types of isotopes. So if they're not telling you the number of neutrons that are present, then you don't have to include the mass number in your symbol. So you still want to recognize that you've got 16 protons and you've got 18 electrons. Okay. Your 16 protons, that's going to tell you the identity of your element. So you know that this is going to be sulfur. It's number 16 on your periodic table. You're also going to look at the difference between the number of protons and the number of electrons. Your protons are positive, your electrons are negative. Here we have 2 more electrons than protons. So we're going to have an overall charge of -2 because we have 2 more electrons and each electron would be like a -1 charge. So to make up our symbol here, we can write our S for our sulfur. You can include the 16 down here if you want, but that's not a requirement. What is a requirement here is to include the charge in the top right corner. And so our charge is going to be -2 for the sulfur. Okay, so you can write it like this, or you can write it like this. Generally, when you're reading charges in like your textbook or when you're trying to write them out and solve them, you want to include the number first and then the symbol second. I know that seems counterintuitive sometimes, and you might switch it around when you're doing your work. I switch it around sometimes too by accident. It's not the end of the world. It's just that usually when you read the charges in a book, you're going to see them written this way. Okay. The next question from our learning check says, consider the elements calcium and chlorine. Oh, let's actually write this a little bit further over here. So we've got calcium and we've got chlorine. And they want us to look at 4 different questions. First question is, identify each as a metal or a non-metal. State the number of valence electrons for each. State the number of electrons that must be gained or lost to acquire an octet. Okay, and then the last question they're asking us to look at here is to write the symbol of the ion. Okay, so if we find calcium on the periodic table, calcium is going to be atomic number 20. Calcium is in the second column. It's in group 2A of our periodic table. That is the alkaline earth metals. So calcium is definitely going to be a metal. Because it's a metal, we know that it's going to lose electrons when it forms an ion, because all metals are going to lose electrons. Chlorine, on the other hand, is in group 7A in our halogen family, and that is going to be a nonmetal. And our nonmetals are going to gain electrons. That's going to help us out to answer these later questions. State the number of valence electrons for each one. We can use our group number to do this. Calcium is in group 2A, so that means it's going to have 2 valence electrons. Chlorine is in group 7A, so that means it's going to have 7 valence electrons. state the electrons gained or lost for an octet. So now with metals, however many valence electrons they have, that's how many they're going to lose. Okay. So calcium has 2 valence electrons. It's going to lose 2 electrons. And when it loses 2 electrons, what it will be left with is a full valence of the electrons that were in the energy level right underneath where these valence electrons were. So when it loses its 2 valence electrons, now it's going to have a full octet. For our nonmetals, they want to gain the number of electrons that gets them up to 8 instead. So chlorine has 7 valence electrons. It's going to gain 1 more electron to get to 8. All right, and then the symbol for each of these is going to incorporate the charge. If calcium has lost 2 electrons, that means it's going to have a positive 2 charge now because it's going to get more positive by 1 for each electron that it loses. Our chlorine is going to get more negative by 1 for each electron that it gains. So chlorine's charge is going to be a -1, or you can just write a minus sign. All right, now let's talk about how ionic compounds form. Okay, so ionic compounds are going to be what forms when you have your anions and your cations come together to form that compound when the two of them are actually like they have that positive negative attraction and they actually pull those ions together. We are going to see that ionic compounds are going to consist of positive and negative ions that are going to be alternating. They're going to have attractive forces between them. These attractive forces are going to be called ionic bonds, and they're specifically between those positively charged cations and the negatively charged anions. Our ionic compounds are going to have extremely high melting points. If you try to melt your cubes like table salt, for example, it's very difficult to do. And they're going to be solid at room temperature. Okay. The NaCl is a good example of an ionic compound. This is what it looks like as a crystal, which is when it's really blown up, which is kind of cool looking. If you were able to look at this on an atomic level, though, you would see alternating sodium ions and chloride ions that they make this 3-dimensional lattice of alternating positive and negative charges. And this is how ionic compounds form. It's just a whole bunch of positive and negative charges that are kind of stuck next to each other based on that charge attraction. When your ionic compounds form, they're going to form based on charge neutralization. Okay. So for example, in your sodium chloride compound, our sodium ion has a positive 1 charge and our chloride ion has a -1 charge. So we have 1 sodium ion that's able to combine with 1 chloride ion, and the overall charge difference is 0. So in any ionic compound, we need to have enough anions and cations present that when we look at the charges that are present, they add up to 0. They should always add up to 0. You should never have any leftover charge in an ionic compound. However much positive charge you have, that's exactly how much negative charge you have. And so sometimes you'll need, 2 cations for every 1 anion if their charges aren't the same number, because the overall charge just has to be the same. Okay. An example of that is something like magnesium combining with these chlorine atoms. Each chloride has a -1 charge. Magnesium has 2 electrons that it loses. So magnesium has a positive 2 charge. So if you have magnesium with a positive 2 charge and each chloride has a -1 charge, that means that 2 chloride atoms or 2 chloride ions are going to need to combine with 1 magnesium ion to make a compound. All right, and that compound would be written that way, MgCl2, which means one magnesium and two chlorines. Okay. So this is the big idea here. The total positive charge that's present has to equal the total negative charge that's present. And that's how you know how many of each ions you're going to need. Okay. So we're going to look at a few examples here. Our first example has us writing out the ionic formula of the compound formed with barium ions and chloride ions. And the way that I would suggest writing this out at first is like visualize it for yourself. For barium, you have a +2 charge, right? Chlorine has a -1 charge. You can even write in the -1 if it helps you visualize. So I want to make the positive charge and the negative charge the same number. So that means I'm going to need two chlorides to give me a total of -2 for every one barium. And the formula I write out is just going to reflect exactly how many of each thing I'm using. So one barium, two chloride ions. My formula is going to be BaCl2. Okay. For the next learning check, they give us a few more to look at. So they give us the sodium ion and the oxide ion. They give us, box this one off. They give us the aluminum ion and the chloride ion. And they give us the magnesium ion and the nitride ion. Okay. So for these, we're going to think about it the same way. Sodium has a +1 charge. And again, you can write in the +1 if it helps you visualize. Oxygen has a -2 charge. So I'm going to need two of these sodiums so that this adds up to +2. And it exactly equals the negative charge, my -2 here that I covered up with my circle. Okay, so +2 -2. So my formula from that is going to show that I have two sodiums and one oxygen. Okay, for my aluminum and my chloride ion, each chloride ion is going to be a -1 charge. Aluminum is a +3 charge. So I'm going to need 3 chloride ions to counteract the +3 charge for my aluminum. And my formula is going to show 1 aluminum and 3 chlorides, AlCl3. For the last one, this one's a little bit tougher because we're going to have to make changes to the numbers of both ions that are present. To get +2 and -3 to a common number, we're going to have to find the least common multiple for between the two of them. And for the numbers 2 and 3, that least common multiple is going to be the number 6. So what I mean is, if you have nitrogen, which is a -3 charge, I'm going to need to add another nitride ion to give me a total of -6. And then I'm going to come over to my magnesium and I'm going to say, all right, well, I'm going to have to add 3 magnesium ions to get to a +6. So I can exactly cancel out my negative charge, right? There's no other way to make +2 and -3 equal to each other. We need to have 2 of the nitride ions and 3 of the magnesium ions to get that common number between them. And then when we write the formula for this, our formula is just going to reflect exactly how many of each ion that we have. So magnesium is going to get a subscript of 3, and nitrogen is going to get a subscript of 2. Okay. Let's look at how we would name these compounds next. Okay, so the typical way that you're going to name an ionic compound, you're going to start by naming the cation, which is going to be your metal, and you're going to follow it by the base name of your anion, which is that first syllable of your anion, your nonmetal name, and you're gonna add that IDE ending to it. Okay, so when you're naming an ionic compound, you name the metal um, just with its regular name. And then the name of your nonmetal is going to be the first syllable of the nonmetal name with the IDE ending. And it's always going to follow the name of your metal. Okay. And you can put a space between them. So these are just some examples. For Ki, K is your metal, iodine is your nonmetal. So to name it, we would name the metal first, potassium, and then we'll take the first syllable of the nonmetal and we change the ending to IDE. So it's potassium iodide, right? This is magnesium, this is bromine. So for the magnesium, we just leave the name alone. For the bromine, we keep the first syllable and we change the ending to IDE, and then the name is magnesium bromide. All right. So let's look at some examples of naming. Okay, we'll start with our K2O. And so the first thing that you want to do is just identify what the cation and the anion are in the compound. The cation is always going to be the thing that's first. The anion is going to be the thing that's second. And we're going to name the cation without changing its name at all. So it's just going to be potassium. And then we're going to take the name of the nonmetal, oxygen. We're going to keep the first syllable and we're going to add the ID ending. So potassium oxide. Okay. We have a few more examples in the next learning check that we can look at. CaO, Al2O3, and MgCl2. Right, so our first element is our cation, so that's going to be calcium. Again, I would recommend that you guys pause whenever we get to one of these learning checks and you try them on your own just before you watch the explanation. The O is going to be our oxygen, so we're going to keep the first syllable and then add the IDE ending. So that's going to be calcium oxide. Here, our cation is our aluminum. And again, we have oxygen acting as our anion. So this is going to be aluminum oxide. And then we have MgCl2. So our Mg is going to be our cation there. It's magnesium. And for our anion, our chlorine, we're going to keep the first syllable chlor and add an IDE ending to that, magnesium chloride. All right. One more example for the next learning check where they have us writing names and formulas for compounds of the following ions. And they have this one presented in an interesting way. So they've given us like some boxes. They give us sodium ion and the aluminum ion. And then the bromide ion, sulfide ion, and then nitride ion. And they want us to make the compounds like kind of go through and match everything up and make the compounds. And then we want to write the formulas and the names for these. So for the first one, we're going to look at Na plus and Br minus. So the formula that this would make would be NaBr because they'd combine in a 1-to-1 ratio, +1 -1. And the name for this is going to be sodium bromide because sodium is our cation and our bromide ion is our anion. For our second example down here, we have the aluminum and the bromide ion. So we'd have Al with a +3, Br with a -1. So we're going to need 3 bromide ions for every 1 aluminum ion. You can like sketch it out for yourself if it makes it easier. That's going to get us our -3 to counteract our +3. So our formula for that is going to be AlBr3. And our name is just going to be aluminum and bromide. Okay. Up here, our next example, we have our sodium ion combining with our sulfide ion. Our sulfide ion has a -2 charge. So we're going to need 2 sodium ions to get enough positive charge to equal our -2. Our formula for that is going to be Na2S. Give ourselves a little more space. And the name for that is going to be sodium sulfide. Okay. And then for our last one in this row, we have our sodium ion and our nitride ion. Our nitride ion's a -3. So now we're going to need 3 sodiums to counteract that -3 charge. So our formula for this one is going to be Na3N. And then the name for that is just going to be sodium nitride. What you're going to notice is that for ionic compounds, and I'll write this again later, but it's worth noting now, ionic compounds never use prefixes to say how many atoms of a particular element there are. Okay, so you'll notice that even if I have 3 sodiums, there's no 3 anywhere in this name. And that's always true for ionic compounds. You never use any kind of prefix to tell you how many different things that are present. Okay. Keep that in mind when you're looking at the names and when you're trying to name them yourself and when you're trying to like pick out the correct names. Our example over here, we have aluminum with a +3 charge, and we have sulfur with a -2 charge. Again, this is a scenario when we're going to need to look for that least common multiple. So we're going to end up needing 2 aluminums to get to +6, and then 3 sulfurs to get to a -6. And so our formula is going to be Al2S3. And then the name for that is just going to be aluminum sulfide. And then for our last example, we're going to have aluminum with the nitride ion. This one's nice because it's aluminum is a +3 charge, nitrogen has a -3 charge. So when they combine, it's just going to be ALN, one of each. And then the name is going to be aluminum nitride. Okay. You're going to notice that for all of these metals, all of these cations that we've looked at for all of these examples, each of them are metals whose charge never changes from compound to compound. They're all metals that you'll find in group 1A, group 2A, or aluminum in group 3A. Not every metal has a charge that stays the same all the time. We have metals, most of them are in the transition group. Some of them are present outside of that transition group, but most of them are in the transition group. And they're going to have charges that change from compound to compound. And we have to have a way to name the compounds that have metals with charges that can change. Um, we have to have a way that makes them distinct from each other. We can't have two different types of like copper compounds forming with oxygen, um, having the same name if they're going to have a same number of like a different number of combination of atoms. All right, I'll show you what I mean in a second. Um, these metals that have a variable charge, like I said, are largely going to be transition metals. The exceptions that you need to know from your periodic table are going to be zinc. Zinc is inside of your transition metal box, but zinc always has a +2 charge. Cadmium, it always has a +2 charge, even though it's inside of your transition metal box. And silver. Silver has a +1 charge, even though it's inside your transition metal box. All of your other transition metals that are inside of that box are going to have charges that change. There are two other elements that you need to pay attention to that are outside of your transition metal box that also have charges that change. Um, I'll show you them as we come up to them later. Lead is one of them, okay? Because you'll notice on the periodic table, if you look up lead, it's number 82 on your periodic table. That's in group 4A. That's outside of your transition metal box. But it still behaves as if it's a transition metal. It still has multiple charges. Tin is another one, SN, number 50 on your periodic table. That also has two charges, +2 and a +4 commonly. And bismuth in group 5A is another metal that is outside of your transition metal box that will still behave like a transition metal. It still has a variable charge. And what you're going to see is that for each of these metals that has more than one charge that it could have, in the name of that metal, there's going to be a parentheses next to it with a Roman numeral inside. And that Roman numeral is going to be the same number as the charge on that metal. So when copper has a +2 charge, it's called copper 2. When lead has a +4 charge, it's called lead 4. Okay. So that's how we're going to differentiate metals that have different charges in different compounds. Let's look at our overall setup for naming these. These are also called type 2 ionic compounds. These compounds that have metals whose charge can change. But what we're going to do is we're going to start by naming our metal, just like we did before. Then we're immediately going to follow it with a parentheses and put the charge in parentheses using Roman numerals. We'll close our parentheses and then we'll follow it by that first syllable of our nonmetal followed by the IDE ending. Okay. These are some examples of the variable charges. The ones that I mentioned to you specifically that fall outside of the transition metal box are going to be bismuth, lead, and tin. Okay, so these things have different charges, even though they are not transition metals. And you do have to know that those three are our exceptions, just like you have to know that silver, zinc, and cadmium always have the same charge, even though they're inside of the transition metal box. A lot of that'll come with practice, though, because you're going to see these things repeatedly. All right, so let's do a few examples here. We'll do this one up on the board, but we have a few examples to look at after this. So they're asking us here to name the MnF2 compound. Okay, so name this. Um, once you recognize that you have a metal whose charge can change, that's when you know that you have to include the charge in the name. All right. Before you can include the charge in the name, you have to know what the charge is. So what you're going to do is you're gonna use the anion to find the charge on the metal. All right. Because the charge on your anion is never going to be different. Like you have a fluoride ion here. That's fluorine is in group 7A. That means that you know the fluoride ion has a -1 charge. And because the formula is MnF2, you know that there's one of these and there's two of these, right? So if each fluorine has a -1 charge, that means that the total negative charge is -2. If there's only one manganese, that means that the charge on that manganese has to be +2 because whatever your positive charge is, it has to equal your negative charge. Okay. So now when you go to write out the name of this, you're going to start by writing the name of your metal, your cation, and this is manganese. And then in parentheses, you're going to write the charge value, but in Roman numerals. And then you're going to follow it by the name of your anion. So we're going to keep the first syllable in fluorine and we're going to add the IDE ending to it. Okay. The next example they give us is to name the compound FeCl2. And let's also name FeCl3. So just so we could see both of those. Okay, so once we recognize the fact that iron is in the transition metal rectangle, we know it has a variable charge. We're going to use the chlorine to figure out what the charge on the iron is. So we have two chloride ions here. Each chloride ion is going to have a -1 charge. So that's a total of -2. So that means that the iron in this compound is going to have a +2 charge because my +2 charge has to balance out my -2 charge. So my name for this compound is going to be iron, and then parentheses 2 chloride. Okay. For my second compound, this one has 3 chloride ions in it. And so again, I can sketch this out. Each chloride is going to have a -1 charge. That's a total of -3. That means that my iron is going to have a +3 charge. Okay, so when I write out the name for this, it's going to be iron 3 chloride. All right. All right, next example. Name the following ionic compound containing a variable charge element. And the compound that they want us to name is SNO2. Okay. They're telling us that the metal has a variable charge. And so we know that we're going to have to figure out what its charge is based on our nonmetal. We have two oxygens. Each oxygen is going to have a -2 charge. And we know that because oxygen is in group 6A on our periodic table. And everything that's in group 6A is going to have a -2 charge as an anion. So if I have two of these oxygens, then my total negative charge is going to be -4. And if I only have one tin, that's going to counteract this -4. My tin is going to have a +4 charge. So then my name for this compound is going to be tin, parentheses, 4 oxide. Okay. Let's look at the reverse process of this. Let me just share the screen for a second. When we're actually taking if we have a name, for example, of an ionic compound and we want to figure out what the formula is, what we're going to see is that the first part of the name tells us the element and the charge. The second part tells us the anion. So if we're going to be trying to figure out the formula from the name, we're going to be able to use this first part where we see like iron 3, copper 1, chromium 2. And this is going to tell us what the charge on our cation is. Okay. So we're going to work through a few of these examples now. The first example they give us, and we already looked at finding the name of this from the formula, but now we're going to see the reverse. If we want to find the formula for iron 3 chloride, okay, like just watch what this process is, because it's like for finding the formulas, it's not bad at all because they already gave us all the information that we need here. The metal name up through the parentheses, this is telling you the name and the charge, or the symbol and the charge of your cation. It's iron, which is Fe, and it's 3, which means it's a +3 charge. For the anion part, it's chloride, which always has the same charge of -1. So now you just have to balance these out like we were doing before. How many chlorides do you need to counteract the +3 charge here? Right? You're going to need 3 of them. So that's a -3 now, and that's a +3. So now they're equal and they're opposite. And the formula that represents that is going to be FeCl3 for our 3 chlorines there. Okay. Our next learning check has us looking at 3 more examples. Nickel 2 sulfide, zinc chloride, and iron 3 oxide. Okay, so for each of these, we can start by writing out our symbols and our charges. Nickel with a +2 charge, sulfide, which has a -2 charge. So my charge numbers are already equal to each other, so I don't have to add any additional ions here. My formula is just going to be NiS. Here for zinc chloride, I need to recognize that zinc, even though it is in my transition metal box, it is going to be one of the metals whose charge is always +2. It's combining with chloride ions, which have a charge of -1. So I'm going to need 2 chloride ions to balance out the +2 charge from my zinc ion. And then my formula should reflect that. 1 zinc, 2 chlorides. And then I have my iron 3 oxide. This first part tells me the symbol and the charge of my iron. My oxide always has a -2 charge. And so now I have to find that common number between them, right? So I'm going to need 2 irons to get my positive charge up to a +6. And I'm going to need 3 oxygens to get my negative charge to a -6. And then my formula is just going to reflect how many of each ion that I used. So Fe2O3. Okay. All right, we're going to look at polyatomic ions next. Your polyatomic ions are special types of ions that form from a bunch of covalently bonded nonmetals. When those nonmetals come together to make their covalent bonds, they have like a leftover charge. Okay, and so it turns them into these charged units, and these charged particles are going to come over and combine with other anions and cations, depending. Most of your polyatomic ions will have a negative charge. Ammonium is the big exception for you to know, because that is going to be our one polyatomic ion on our list of polyatomic ions to know that has a positive charge. All of the rest of our polyatomic ions that we're going to look at are going to have a negative charge. NH4 plus is called ammonium. Just you have to be able to recognize these polyatomic ions on site. So it's best to get to know them as soon as possible. This is just showing you some examples of different polyatomic ions. Here's our list of names and formulas for these. Again, you do have to know these. You have to know the names and the formulas of these. You have to be familiar with them. You have to be able to recognize them within compounds. Because when they're parts of compounds, if you have to like name a compound that has a polyatomic ion, it's not going to make, like, what you're seeing won't make sense to you if you can't recognize that it's a polyatomic ion. Okay, so you have to spend some time getting to know these polyatomic ions, getting to know the names and the formulas of them. You can see the way that they're grouped here. They're trying to group them for you based on the main nonmetal that is like the focus of the particular polyatomic ion. That focus main nonmetal is usually found somewhere in the name of the polyatomic ion. So you see like the sulfur, sulfate, sulfate, sulfite, sulfite, phosphorus, phosphate, 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 phosphite. So you'll see that kind of similarity there. Some things to consider when you're looking at your polyatomic ions. The names of most of your polyatomic ions are going to end with an ATE. So like sulfate, phosphate, nitrate. When you have sets of related polyatomic ions, so related means something like this one, SO4 with a -2 charge and SO3 with a -2 charge, right? Those are related to each other clearly. They're almost the same formula. The only difference is that sulfate has 1 more oxygen and sulfite has 1 less oxygen. So when you have sets of related polyatomic ions, the polyatomic ion that has 1 less oxygen the ending of that ion is going to be ITE instead of ATE. So that's why SO4 2 minus is sulfate and SO3 2 minus is sulfite, because sulfite has one less oxygen. Phosphate with 4 oxygens has an ATE ending. Phosphite with 3 oxygens has the ITE ending. Okay, that's the relationship there. The only polyatomic ions that you're going to see that do not end either in ATE or ITE are going to be the cyanide ion and the hydroxide ion. Okay, these are the 2 exceptions to that ending rule. But both of these ions are important, so make sure that you know their names. You're also going to see a relationship between adding a hydrogen ion to a polyatomic ion. It's going to change the name and the charge of that particular ion. So if you look at CO3 with a -2 charge, this is called the carbonate ion. If we add a hydrogen ion to CO3 2 minus, the new formula for that is HCO3 with a -1 charge. So our CO3 stayed the same, but we added a hydrogen and our charge got positive by 1. Okay. The name of this is going to change to hydrogen carbonate, or in more like common naming, bicarbonate. The same thing happens with our sulfate ion. We have SO4 with a -2 charge. If I add a hydrogen ion to it, it becomes HSO4 with a -1 charge. So we added a hydrogen and we removed one of our negative charges. And the name of this is going to be either hydrogen sulfate or bisulfate. But you'll see that, if you go back to our chart, you'll see that repeated, right? You have the same patterns throughout the table of your polyatomic ion names. They're not just random names, even though it might seem random at first. We'll also see some sets of halogens that are in group 7 that form a series of 4 polyatomic ions. Each polyatomic ion is going to have, it's going to decrease in the number of oxygens by 1, or increase if we're going in this direction. But they're all different from each other by 1 oxygen. The charge doesn't change. The halogen and the oxygen, like the identity of the elements, doesn't change, but the number of oxygens in each one is the thing that changes. So the ion that has the least oxygen is going to have a prefix of hypo, and it's going to end with an ITE ending. So the ion that comes next that has 1 more oxygen than that is going to lose the hypo prefix, but it's going to keep the ITE ending. When we add 1 more oxygen to that, our ending is going to change from ITE to ATE, just like we saw before, where something has more oxygen, so it has an ATE ending. And then for the ion that has the most oxygen, we're going to add a prefix to that, and we're going to keep the ATE ending. This prefix, PER, means more than. So when you're calling this ion the perchlorate ion, you're literally saying that this ion has more oxygen than chlorate, which it does, because chlorate has 3 oxygens and this has 4. For your hypochlorite ion, hypo means less than. So when you call this ion the hypochlorite ion, you're saying that it has less oxygen than the chlorite ion, which it does, because we have 2 oxygens here and just 1 here. Okay. Now, in terms of using our polyatomic ions, we're going to use them the same way that we used any other ion. Our polyatomic ions have an overall charge, and that overall charge is still going to have to balance out with the charge of the other ion that makes up our ionic compound. We still need that charge balance. So the example that they're showing us here is making the formula for magnesium nitrate. We know that the magnesium ion is going to be a Mg with a +2 charge. And we know that each nitrate is going to have the formula of NO3 with a -1 charge. So we're going to need 2 nitrate ions to get an overall charge of -2 to balance out the +2 charge from the magnesium. And the formula that we write down has to reflect that. It has to reflect that we have 1 magnesium and we have 2 nitrate ions. Okay. When you have more than 1 polyatomic ion in your formula, you're going to place parentheses around them so that when you put the subscript outside of the parentheses, you're showing that you have 2 of everything inside of the parentheses, right? You don't want to attach a subscript to just another subscript. So that 2, that subscript of 2 is going to apply to everything that's inside of the parentheses there. Okay. So let's look at a few examples. First example is to find the formula for aluminum hydrogen carbonate. And so you start your process the same way as we did for the other compounds. You look at the name and you pull the ions from it. Aluminum is Al with a +3 charge. Aluminum always has a +3 charge. Now, at this point, you're going to have to start looking at your polyatomic ion table and learning the formulas and the charges for these. The hydrogen carbonate ion has a formula of HCO3 with a -1 charge. Okay. So I have a +3 charge here. I have a -1 charge here. So I'm going to need 3 of these things. To make my negative charge equal to my positive charge. Okay. When I go to write down my formula for this, it has to reflect 1 aluminum and 3 hydrogen carbonate ions. When I go to write down that I have 3 hydrogen carbonate ions, I'm going to want to keep my hydrogen carbonate inside of these parentheses so that when I put my subscript of 3 next to it, I'm saying that I have 3 of these things. Okay, that's what my parentheses do. And that would be my formula for that. Let's look at another example for sodium phosphate. Okay, so again, we look at each cation and anion and we find the formula and the charge for each one. Sodium always has a +1 charge. Our phosphate ion is going to be PO4 with a -3 charge. And so when we look at that charge difference, we're going to say, all right, well, I need 3 sodium ions to add up to a +3 to counteract the -3 charge from my phosphate ion. And then you know that your formula is going to be Na3PO4 because you have 3 sodiums and 1 phosphate ion. All right. Let's look real quick at the slide for naming ionic compounds that have polyatomic ions in them. I just want you to see the visual here before we look at some examples. The overall process isn't any different than when we were naming other ionic compounds. It doesn't change any. But you are seeing these polyatomic ions now instead, which, you're not looking at the names of elements in this case. Um, Important things to note is that when you have ionic compounds with polyatomic ions, that usually the first ion is going to be a metal, unless you have the polyatomic ion ammonium present, which is going to be our only positively charged polyatomic ion. Usually you're going to find your polyatomic ion acting as an anion. So you're going to usually find it in that second position, in the anion position. Okay. The biggest part of working with polyatomic ions is recognizing them. That's why it's so important that you take the time to remember them and that like work with that table. Set up flashcards for yourself. Set up something like on Quizlet so that you can quiz yourself. I'm sure like there's pre-made Quizlet units on polyatomic ions already, but any of that is going to be helpful for you in terms of recognizing the names and the formulas. And then just like with any other ionic compound, we don't use prefixes when we're naming ionic compounds. So what we have here, Na2SO4, this is our sodium ion, this is our sulfate ion. So the name of this is just going to be sodium sulfate. Okay. For the compound FePO4, we know that the phosphate ion has a -3 charge. We know that iron is a metal that can have many different charges. So if phosphate is a -3 charge and there's only one iron, that means iron has to have a +3 charge. So the name for our compound is going to be iron 3 phosphate, right? We don't change the name of the polyatomic ion at all. We write it exactly as it's called in our table. That's one difference between what we did before and what we're doing now with the polyatomic ions. When we have an element that's part of our ionic compound, our element that's the anion changes the ending of its name. But our polyatomic ion endings, they don't change. They stay as they are. For our last example here, we have aluminum atoms and we have the carbonate ions. And so the name of this is going to be aluminum carbonate. All right. These are just some examples of formulas that have polyatomic ions in them and then their corresponding names. These would be good to look at just as getting yourself used to identifying polyatomic ions. But let's take a look at some of these examples. So they want us to write the correct formula for from each name for starters. Okay. And so for each one, we'll start out by writing the symbol and the charge for our cation. And then for our anion, the nitrate ion is NO3 with the -1 charge. Aluminum is a +3 charge. So we are going to need 3 nitrates for every 1 aluminum. So the formula for this is going to be Al, and then in parentheses, NO3. Then we'll close our parentheses, and then we're going to write the subscript, which represents the number of nitrate ions that we need. Okay. Our second example, we have a transition metal. So they're telling us the charge of it. So it's copper with a +2 charge. You have the nitrate ion again. So in this case, we're only going to need 2 nitrate ions to counteract the +2 charge from our copper. And our formula is going to be Cu, then parentheses, NO3, close our parentheses, and we have 2 of those. We'll box off the ones that are done. For our next example, we have iron 3 hydroxide. So our iron is going to have a +3 charge, and we have our hydroxide ion. Each hydroxide ion has a -1 charge. So we have a total of -3 there. And so our formula for our iron 3 hydroxide is going to be Fe, and then in parentheses, OH for our hydroxide ion. And we have 3 of them. Okay, and then we have tin 4 hydroxide. So the symbol for tin and the charge for tin. Hydroxide's -1. So we're going to need enough hydroxide to counteract that +4 charge. So our formula for this is going to be Sn, and then in parentheses, OH4. Okay. Let's try to name some polyatomic ions, not some compounds with polyatomic ions from the formulas now. So we're going to name the following ionic compounds. Okay, we have CaNO3 2, and we have FePO4. When you're naming an ionic compound, now we have practiced with both metals that have only one charge and metals that have multiple charges. Before you can name an ionic compound, you have to identify whether your metal's charge can change or not. Okay. So for both of these, before I do anything else, I'm going to look at my metal and I'm going to decide whether it only has one charge or more than one charge. Calcium is in group 2A. It only has one charge. It only has a +2 charge. So when I go to name this, I don't have to worry about including the charge in the name. The name of this compound is just going to be calcium, which is the name of the metal, and nitrate, which is the name of the polyatomic ion. For our second example, though, we have FePO4. Fe has more than one charge. So I'm going to need to use the charge on the phosphate to figure out the charge on the iron. Phosphate has a -3 charge. So that means if I only have one iron that's combining with it, that iron must have had a +3 charge. So for this compound, I'm going to name my metal, and in parentheses, I'm going to include my charge, and then I'm going to name my polyatomic ion. Okay, iron 3 phosphate. We have a few more to try. MgSO3, MgSO4, Pb3, PO3, 2. Okay. But we start off the same way with each one of them. We look at our metal. Is it one charge or more than one charge? Magnesium is in group 2A, so it's going to have one charge only. It's always going to be a +2 charge. And that means that we do not have to worry about including its charge in the name. So when we name this, we're just going to name the metal, magnesium, and then the name of the polyatomic ion, SO3, is going to be the sulfite ion. Okay. For our next example, we've already decided that magnesium only has one charge, so we can just use the name of the metal. This time it's attached to the sulfate ion. All right. Down here, we have lead. Lead has more than one charge. And so we're going to need to figure out the charge on the lead before we can do anything else. Okay. You'll have to look up your phosphite ion. PO3 is phosphite. I know that it's hard to get used to these at first. Your phosphite ion is going to have a -3 charge. We have two of them. Okay. So that means that our total negative charge is going to be -6. We have 3 lead ions. And we have to make sure that all of those lead ions add up to a +6. So that means that each lead is going to have to be a +2 so that it adds up to a +6. Okay. So when we go to name this compound now, we're going to write the name of our metal. In parentheses, we're going to include the charge on the lead, so charge of 2. And then we're going to name our polyatomic ion. Okay. Let's look at one more set of examples for this section. Okay. So again, we're going to start each of these by identifying whether our metal has more than one charge. Iron definitely has more than one charge. So we're going to have to figure out its charge before we can name it. We have 3 sulfate ions. Each sulfate ion is going to have a -2 charge. So the total there is going to be -6. And our compound has 2 irons. So those irons have to add up to a +6. So that means that each iron is going to have a +3 charge so that they can add up to a +6 and counteract the -6 charge. Once we know that, we can name it. It's going to be iron, and then in parentheses, 3. And then this is our sulfate ion. So iron 3 sulfate. For our next example, our metal is barium. Barium is in group 2A. Barium only has one charge. So we do not include its charge in the name. No parentheses for barium. When we name it, it's just going to be the name of the metal and then the name of the polyatomic ion. Okay. And then our last example, we have nickel. Nickel is in our transition metal box. It's going to have more than one charge. And so we see that we have 1 nickel and we have 1 carbonate ion. We know that our carbonate ion has a -2 charge. And if we only have 1 nickel to counteract that charge, then our nickel ion must have a +2 charge. And so then the name of our compound is going to be nickel 2 carbonate. Okay. That's the end of this section. We'll come back with the next video and we'll start to talk about the molecular stuff.